My name is Pavel. I'm a Imav Society president. The society was started by 3 PhD students to bring unmanned aerial systems to students like myself. I'm currently in my 4th year aerospace engineering degree, and basically we started off by taking part in electric lift challenge competition here in UK, and since then 2 years ago society has grown and we decided to take next step in development of the society, so that's taking part in a little bit more advanced competition like Imav.
Hi, my name is Bagat Rasha and I'm the project manager and the chief engineer of the University of Manchester UAV Society. This year this is our first entry for an autonomous UAV competition. Past years we were engaged in British Model Flying Association competitions. This year we wanted to do something more challenging, and we started preparing for the Imav 2014 competition. We had a team of around 15 people from all undergraduate students from computer science, electrical electronic engineering and aerospace engineering. Our strategy was the following. We have focused on doing the mapping first and number recognition. We have done mapping and most of the number recognition, and I can say 10% of the indoor navigation. In the coming months we're going to finish the indoor navigation and the number recognition. Now I'll show the quadcopter which we use for mapping. This quadcopter is using the Pixel autopilot here with the 3DR GPS. For the mapping, we had used the camera, the NX1100 camera, without the gimbal, brushless gimbal. But now we've installed a brushless gimbal, but it's not fully complete yet. We haven't tested it yet, and the legs need a bit of extension. We had used the timer for taking interval photographs. Yeah, and we used two 4400 mAh batteries here. Here you can see this is the result we got. We took photos and we stitched them with the help of Photoscan Professional Agisoft software. This is what we got. We will be trying to improve on it. That's all about mapping. I can say we've 95% finished the task. Now I'll show you the quadcopter which we will be using for a number recognition. We have 2 more which is currently in progress. In the following section you will see how our number recognition works on a computer. Our next step will be to transfer the software to a BeagleBone computer and place the BeagleBone computer on this and use a webcam camera to scan the numbers. We will also be using FPV cameras on all the quadcopters we use for safety, to monitor where the quadcopter is going. And additionally, we will also be flying this fixed wing higher than all of the quadcopters. So we have one video showing from top all the quadcopters, where all the quadcopters are and what they are doing, just for monitoring purposes. Initially we're going to just transmit the video, but later we might be able to do it this year. We want to make this as a commander aircraft so that it will be able to control the other small aircraft as well. So in case if something goes wrong, the commander aircraft can also give a signal. Speaking of if anything goes wrong, we're also going to use a GPS failsafe, which is automatically engaged in Pixel autopilot. Basically, if it loses GPS for more than 5 seconds, it's going to land wherever it is. We're going to use battery failsafe. If the battery runs low, it's going to initiate an RTL, return to launch, or if it is too low, it's just going to land wherever it is. We're using Pixel, so obviously we have the safety switch. I can show it on this quadcopter. We have the safety switch here. So if this switch is now this safety switch is off, which means it's in safe mode, and this is the safety switch is off. Now we can arm it. This is to prevent personal injury. We're going to use 5.8 gigahertz for FPV transmission, and we're going to use 2.4 gigahertz for radio control. So in summary, I can say we have finished 95% of the mapping task. We have finished about 50-60% of the number recognition task. You will see in the later video how the number recognition works on a computer. And then I can say about 10% of the indoor navigation is done. So we will be using this 9 degree of freedom Razer IMUs in conjunction with the ASUS 3D camera sensor for a triangulation sensor. We're going to use these two to drive an SLAM algorithm for indoor navigation. We have used previously the OpenCV libraries to change. There was an OpenCV library which would recognize fruits, so we've changed that to recognize a human being. So we're going to gradually improve and make a SLAM algorithm in which it detects landmarks and it records the position of the landmark and then it moves on. So that's going to be most of our work in the coming 2-3 months is going to be in the SLAM algorithm. We're going to try and make it fly indoors.
My name is Carlos. I'm doing aerospace engineering. I'm in my third year now.
My name is Kirill Kuldiashvili. I'm studying computer science and mathematics.
Hi, I'm Antonio Sanchez.
I'm Sahan Najafzadeh, a third year physicist.
Hi, I'm Ben Lewis. I'm an aerospace student, first year, and I joined the UAV Society this year. And I joined the Imav team, working on number recognition currently. And the reason that we're working on this task is it's part of this Imav international competition. And the benefit, the way that we've been going about it is we've methodically analysed the problem from several different angles and looked at which different ways we'd end up doing it. So we chose the BeagleBone hardware platform to do our computational calculations for the competition, given that it's really powerful and relatively low cost and very light and appropriate for such use. We then decided that we were going to use a high-resolution camera for mapping from the other teams, and our team for this number recognition first looked at OCR, so optical character recognition that is, to establish a way of reading these numbers that are displayed on a board at the competition. But we worked out that would be rather ineffective, given that OCR is normally targeted at recognizing many different kinds of different characters, and so given a very convoluted environment with things other than letters and numbers, it tends to read wrong information and also to not pick up on the correct information. So we designed a custom algorithm that one of the teammates and me have been working on, working on the BeagleBone, which basically uses a set of templates based on the images that they will provide, the numbers that they will display, and as a result we can then read those numbers very easily and get very high accuracy results on what numbers are displayed and read them back to the user. And we're now working on an algorithm to basically establish whether this number has changed in the last 30 seconds, given that the numbers will change every 30 seconds. We want to establish what, we can find any false positives very easily by taking several photos and comparing them, and we can also find out sort of disqualify any period where the numbers have been changing over so that we get the best results. So currently we have an algorithm which can read the numbers exactly as specified in the competition, and it works perfectly in MATLAB on the desktop using university licenses there. And we're now sort of working on two different ways of getting this to run on the BeagleBone. Firstly, they've been having some minor issues with porting it to C, C++. in terms of getting the programming running that way on the BeagleBone, because some of the functions that they've used to process the images are not supported by their cross-compiling system in MATLAB. And so we've also been working on another attitude of doing it using Octave, which is a open source MATLAB equivalent, which can run directly on the BeagleBone. But that equally has some problems we've found recently, so we're working on that too.
So we've done as number recognition, and the way we do it is we filter the image using the HSP colors, and we filter a specific the specific color of the image, and then on the filter image that we can see here, we apply segments as segment recognition to find all the contours in the filter image. In here you can see, so now you can see how when we introduce a new hand, a new object, it doesn't show. And when we introduce a new object that is recognized, so in here you can see all the different objects it has found. So all the 6 segments of the 0 plus some 2 because of a bad recognition. Then based on the number of segments and the position of the segments, we decide which number it is, and we print it.
No.
My name is Ismail Ramzan. I've been working as part of the team called the MMS, which is the Mission Management Systems. I've been the manager for that team. We handle the pre-flight and the post-flight processing. So 2 tasks that I've worked on myself were, one of them was calculating the altitude we have to fly at based on the specifications of the different aircraft the team's going to be using to carry out the mapping exercise. And then also the post-processing of the images to generate an orthomosaic map of the area that we can then use to identify road blockages. Some of the challenges we faced with this, of course, were the parallax errors you're going to get when you actually just take the pictures above, because if you fly over a table, you're also going to capture the side. So we used our data to then generate a 3D map, and then from that 3D map, then generate a 2-dimensional map. We've also faced challenges, for example, with the processing time, because this is such a processing demanding task. It takes a long time to do it. However, we don't have that much, so we've been trying to develop more efficient processes more efficient ways of doing this task. We've assigned people different areas of the task. So, for example, when we did the calculations behind the altitude, that was more of everyone get together and suggest their own ideas on how we can actually create a formula that allows us to determine what altitude we need to fly at and make sure we consider all the different factors that would affect us. When it came to the mapping, we had different people working with different pieces of software to try and find the most efficient solution to the problem. So we've had people looking, for example, at Agisoft, which is a paid-for version of which does the same sort of thing as Visual SFM, which I've been working on. However, we don't know which is going to be more efficient. We've also had some more abstract suggestions where I've assigned people to work with programs such as Hugin to try and find if there's a way to do that, where they were then going into, I forgot what it's called because I didn't work on it myself, but it's this program which allows you to get street maps of the area, so it will remove data except for the roads, and then the images can be stitched on top of this map of roads based on the roads that they have in the images themselves. Now, although we gave up on this solution because although it is reasonably effective, it's not very efficient, and of course you need roads within the area, and the area we have for Imav only has a few roads. It's not exactly a dense urban area, it's just a village, so we had to scrap that idea. I think the one we're going to go with probably is Visual SFM or Agisoft, depending on which performs better, because they're both very similar processes. They both generate a three-dimensional map and then convert that into a two-dimensional one.
Hey, I'm Dimitris, and I'm a first year aerospace engineering student, and I've been with the UAV Society for the past 2 years, and this year I've been working on the Imav project. Because I have an aerospace engineering background, I have worked on the construction and design of the quadrotor, but I also have a strong interest in embedded systems and robotics, so I've worked on the development of a novel SLAM algorithm for navigation in indoor spaces. For this task, I had to study a lot about computer vision practices and how we can obtain the images we need, the data we need for the quadrotor to process on. I did work on the development of a SLAM algorithm for the quadrotor in order to navigate in the indoor environments. In order to accomplish this task, we use an infrared camera to obtain the necessary data, and then we process the data on an onboard computer, and we feed the data back to the autopilot, so we have a full closed loop system for indoor navigation. It's been quite challenging during the first few months to get on track because I'm an undergraduate, so I don't have much the background that many other contestants in the competition have. But I have worked quite hard, and now I think I'm at a good level. I'll continue to work more over the next few months and during the summer when we don't have school. But I think by the time of the competition, we will be at a pretty good level.
There'll be a number of different numbers that will go into it, and it isn't. Yeah, so it's
No, that's not.
I don't know how to do it. We do that. Yeah, we try that.
Indeed. Auto mode.
Is it going?
Yes.
Good.
It is. Okay, maybe we'll set it a bit too far away. 10 meters. Pass waypoint 1.
9.
We're gonna tell you count 5. Wait. 1, 2, 3, 4, 5. Okay, try to do it. Again, now what's the critical part? Be ready. They were reaching waypoint 3.
So it's going to wait then land, yeah?
Yeah. Loiter 10 seconds. Yeah. So count 10 seconds from now. 2, 3. And it should land, it should go down to 3 meters.
At the same spot or?
Now you can actually going down. Carefully. 8 meters. 7, 6, 80, 6, 550, 480, 3,
320, 304, 254, 165, 150, 0.9, 0.8, 1. Actually, 100.
Is that 20 meters?
This is pretty much what we have done in preparation for the 2014 Imav. Initially, our progress was very slow because this was our first autonomous competition. We didn't have much idea about autopilots and automatic control and FPVs. We really hope to qualify for the competition. We are confident that we will put up a good show because we have progressed quite a bit. And also it will be a good experience for us to learn a lot from such a high-level competition. About 16 of us have been working for the past 1 year, and a lot of money and effort has been put into this. And we'll be really happy if you could qualify. Thank you for listening, and if you have any questions, you can always contact us.